Hello guys, my name is IBM. This is part 3 of Feb March 2025 paper 2-2. I think this is going to be questions 5 to 7. Questions 5 to 7, this is part 3. Without wasting time, question 5. A stationary loudspeaker emits sound of constant frequency. The microphone is placed near to the loudspeaker and connected to a cathode ray oscilloscope. The trace on the CRO of the trace on the screen of the CRO is shown here. So we have a loudspeaker somewhere here. Let me sketch a loudspeaker. And we have a microphone placed somewhere here. The microphone is connected to a CRO. A CRO, I normally encourage my students to represent a CRO, something like that. Okay. The time base of the CRO is set to 5 times 10 to the power of minus 4 seconds per centimeter. The speed of the sound emitted by the loudspeaker is 330 meters per second. Determine the wavelength of the sound. So we know that speed equals to lambda times f, or we know that f equals to 1 over period. And of course, the time base, the period t is going to be the length representing 1 cycle on the trace times the time base setting x. I always use x for time base setting. The length representing 1 cycle from the graph is, let's check. So 1 cycle stops about here. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4. So this is going to be 5.8 centimeters. This is 5.8 centimeters. So the length of 1 cycle is 5.8 centimeters. The time base setting x is 5.0 times 10 to the power of minus 4 seconds per centimeter, which means that the period is going to be equal to 5.8 times 5 exponent minus 4. That is 2.9 times 10 to the power of minus 3 seconds. Then the frequency, of course, we want to find the wavelength. So the period is that. We know that speed v equals to lambda times frequency, which is lambda over t. Therefore, the wavelength is going to be v times t, which is going to be v is 330 times the period, which is 2.9 times 10 to the power of minus 3. So we have 330 times 2.9 exponent minus 3. Of course, v is equal to lambda over t because we know that frequency is 1 over t. So this is giving us 0.957. 0.957 meters. The loudspeaker now moves in a straight line. It moves in a straight line while emitting the same sound of constant frequency. So the loudspeaker is moving and is producing a constant frequency. The period of the trace on the CRO increases continuously. Remember, the CRO detects frequency which is arriving to it. So the CRO is acting as the observer. Describe the motion of the loudspeaker. Because the period on the trace of the CRO increases continuously, we get an impression that the frequency detected frequency is going to be decreasing continuously, because we know that frequency is equal to 1 over period. So if the detected period is increasing, it means the detected frequency is decreasing. And if you look at the formula frequency, observed frequency equals to v over u over v plus or minus u of the source, then times the source frequency. This is observed frequency. Since the detected frequency is continuously decreasing, of course, for moving away from the observer, f naught is going to be equal to v over V plus US then times Fs. So because the detected frequency is continuously decreasing, chances are high that the source is moving away at an increasing speed because V is constant, that is the speed of the waves, and if US is the speed of the source. So the speed of the source must be increasing or the source must be accelerating. Therefore, we can say that increasing period increasing increase in period, let me say increase in period, increase in period, increase in period on the CRO means decrease in the detected, not in the produced frequency by the source, but in the detected frequency. In the detected frequency. So the loudspeaker, of course, when the detected frequency is smaller, it means the object is the source must be moving away or the observer must be moving away. So since the loudspeaker is the one which is moving, so the loudspeaker is moving away. Is moving away from the microphone, and because the period increases continuously, it means the frequency also decreases continuously. So the loudspeaker is moving away from the microphone at an increasing speed. At an increasing, if he was moving at a constant speed, then the frequency would be just less, would decrease to a constant value. But because it's moving, the period is increasing continuously, then the frequency must be decreasing continuously. Therefore, the speed must not be constant. So the speed must be increasing. So it's moving away. I almost wrote or aways. Is moving away from the microphone at an increasing speed. Or you can say whilst accelerating. In other words, the loudspeaker is accelerating away from the microphone. Okay. A cylindrical copper wire P of length 0.24 meters is shown in the figure. The current is 0.8, the resistance is 3.3 milliohms, total number of charge carriers N in the wire is 2.6 times 10 to the power of 22, resistivity Rho is 1.8 times 10 to the power of minus 8 ohm meters. Calculate the potential difference between the ends of the wire. Of course, the potential difference V is going to be I times the resistance of the wire, which is going to be 0.85. The resistance of the wire is 3.3 times 10 to the power of minus 3 to remove the milli. So you have 0.85 times 3.3 exponent minus 3. So that is 2.805 times 10 to the power of minus 3, which is the same as 2.8 times 10 to the power of minus 3 volts. Show that the cross-sectional area of the wire is 1.3 times 10 to the power of minus 6. You and me know that resistance of a conductor of a wire is rho L over area, and which this therefore implies that the area is going to be rho L over resistance Resistivity is given as 1.8 times 10 to the power of minus 8 ohms. The length of the wire is 0.24. Divide by the resistance of the wire, which is 3.3 times 10 to the power of minus 3. So we have 1.8 exponent minus 8 times 0.24 divided by 3.3 exponent minus 3. So that is 1.309 times 10 to the power of 6 minus 6 meters squared, which is approximately 1.3 times 10 to the power of minus 6 meters squared. Show that the number density of charge carriers in the wire is 8.3 times 10 to the power of 28 per meters cubed. The number density is normally given as small letter n. So the number density is equal to the number of charge carriers divided by the volume of the wire. Or you can say that is capital N divided by V, where V is volume. So N was given as 2.6 times 10 to the power of 22. And then volume is cross-sectional area times length. Volume is cross-sectional area times length. We know that so this means N is the same as capital N divided by cross-sectional area times length. So volume, this is going to be cross-sectional area, which is 1.3 times 10 to the power of minus 6, then times the area, that is the area times length, which is 0.24. Answer. So you have 2.6 exponent 22 divided by open brackets 0.24 times 1.3 exponent minus 6. So that is 8.33 recurring times 10 to the power of 28. 8.333 times 10 to the power of 28 per meters cubed, because this one is meters cubed. So this is approximately 8.3 times 10 to the power of 28 per meters cubed. Remember, the examiner wants always to look at the answer which rounds off to what has been given for questions which ask you to show that. Calculate the average drift speed of the charge carriers in the wire. Average drift speed. We know that current equals to never, or you can use NQVA, where V is the average drift speed. So this implies that the average drift speed is going to be I divided by NQA. The current was 0.85 divided by N. N is 8.3 times 10 to the power of 28. Then Q, the charge carriers are electrons. So because they said they are electrons, the charge of an electron is 1.6 times 10 to the power of minus 19. Then the area, cross-sectional area, is 1.3 times 10 to the power of minus 6. Okay, let me first combine the denominator. 8.3 exponent 28 times 1.6 exponent minus 19 times 1.3 exponent minus 6. Then we get a 0.85 divided by the answer. So that is 4.92 times 10 to the power of minus 5. 4.92 times 10 to the power of minus 5 meters per second. So the answer here is approximately 4.9 times 10 to the power of minus 5. Alternatively, when you look at the formula I equals to NQVA, you may remove N. This will be number of particles divided by the volume, which volume is cross-sectional area times length, then times Q times V times A. So A cancels out. That means I can find the drift velocity V from V equals to I times L divided by N times Q. When I substitute, the current was 0.85, the length of the wire was 0.24, divided by N. I think they gave us N as 2.6 times 10 to the power of 22. Then the charge is 1.6 times 10 to the power of minus 19. We can check this. Starting with the denominator, 2.6 exponent 22 times 1.6 exponent minus 19. So I'm going to open bracket 0.85 times 0.24 divided by the answer. So again, we have 4.9 times 10 to the power of minus 5 meters per second. So this would be another alternative. A different copper wire Q has the same volume as wire P, but non-uniform radius as shown in the figure. The radius R1 at the end X of wire Q is the same as the radius of wire P. Radius R2 is less than R1. Okay, so because wire P had a constant radius, so they said state and explain how the resistance of wire Q compares with the resistance of wire P. So first of all, I will say that wire P, because it had a constant radius, constant cross-sectional area, I will say wire P has a constant resistance throughout. Wire P had a constant resistance throughout. But then they say the volume is the same. Remember, volume is equal to cross-sectional area times length. And we know that resistance C is equal to rho L over cross-sectional area. And since area is V over L, resistance is going to be rho L over V over L. That means resistance is going to be equal to rho L cubed divided by the volume. So from the formula volume equals cross-sectional area times length, each of us should be now seeing that as cross-sectional area decreases, because the radius is decreasing, the length L must increase if the volume is to remain the same. So for the same volume, as cross-sectional area decreases because the radius is decreasing, then the length must increase. Which means, therefore, that the length of wire Q is going to be greater than the length of wire P in the first case. But since the cross-sectional area is becoming smaller, we know that resistance is inversely proportional to cross-sectional area. So even on average, if you get the cross-sectional area of this plus the cross-sectional area of this and divide by 2, on average, the cross-sectional area of wire Q is smaller than the cross-sectional area of wire P, because the cross-sectional area of wire P is actually constant. Here, on average, the cross-sectional area is going to be smaller because it is decreasing uniformly, so we can get the average cross-sectional area. So we can simply say that for the same volume, as as area decreases, as area of Q decreases, the length increases. So it means length of Q is greater than length of P. That's number one. For the same volume as area of Q decreases, the length increases. So length of Q is greater than length of P. But of course, we know from this equation here, from resistance equals to rho L over A, we see that, oh, by the way, I should also talk about the average cross-sectional area of A being smaller than that of B, or I can say R is directly proportional to L, so resistance increases, and R also is inversely proportional to the square of the radius. So because the radius, since R decreases, or the cross-sectional area decreases, the overall resistance of Q increases along the wire. But I'll just consider the average cross-sectional area. Now let me just consider this. So from R equals to rho times L over A, and the average cross-sectional area of Q is less than for P. Let me say R, I'll just say R equals to rho times L over A, and average cross-sectional area of Q is less than for P. Why should I say? I want correct grammar. So L, length of Q is greater than length of P, and the average cross-sectional area of Q is less than for P. But resistance is proportional to the length per unit area. Length per unit cross-sectional area is proportional to the length per unit cross-sectional area. Hence, resistance of Q is greater than that of P. So I want to throw more light on this. So if resistance is equal to rho times L over A, Now that length of Q is greater than length of P, so it means resistance of Q is most likely going to be greater than resistance of P depending on length. But also cross-sectional area, average cross-sectional area of Q is less than average cross-sectional area of P. That means the length per unit cross-sectional area for Q is much greater than the length per unit cross-sectional area for P. Therefore, the resistance for Q is going to be greater than the resistance for P because the length per unit area of Q is greater than the length per unit area of P. That is simple analogy. On the figure, sketch a graph of the variation of average drift speed of the charge carriers with distance from x average drift speed. So we have already seen that the average drift speed V equals to I divided by NQ times A, NQ times A, which is the same as, of course, we know that area is pi r squared. So this is I divided by NQ pi r squared. So of course, if the current is constant, N is constant, if Q is constant and pi is constant, it means that the average drift speed is inversely proportional to r squared. And as x increases, r decreases. So if as x increases, we have seen that the radius decreases, and as r decreases, v increases. But because note that r is squared, so that means this cannot be a straight line. So as x increases, r decreases. As r decreases, v increases according to this equation here. So that means the drift speed is going to be increasing, but because it is 1 over r squared, then this is going to be an exponential graph. In other words, because v is inversely proportional to r squared, it means v increases more rapidly as r decreases, or v increases more rapidly as the distance increases. So this is going to be a graph of increasing gradient. So this is going to be a graph of increasing gradient. Okay. And lastly, an isolated nucleus Q decays into nucleus R and an alpha particle. Of course, you and me know that an alpha particle is written as alpha 42. Okay. The alpha particle has speed of 1.5 times 10 to the power of 7 meters per second. Complete the equation for this decay. Okay, so we just balance. Of course, by conservation of proton number, we have that 88 is equal to x, or let me say z, plus 2. Z plus 2, which means that z is 88 minus 2, which is 86. So here we have 86. Then for nucleon number, we have that the nucleon number A on the left-hand side should be equal to 222 plus 4, which is 226. So this is going to be 226. By considering momentum, calculate the speed of the nucleus R after the decay. Of course, before the decay, it was isolated and stationary. We know that momentum is mass times velocity. Before, total momentum is 0. After, by conservation of momentum, total momentum after is going to be, so the mass of this is 222 times the mass, which is u. 22u, that is the mass, times the speed, which we don't know, let's call it v. Then plus, for the alpha particle, its mass is 4 times u. Then times the speed of the alpha particle, which is 1.5 times 10 to the power of 7. Of course, this side, I would have said 22u times 0 because it was at rest initially. Maybe let me put that one this side. Before collision, before splitting, the mass on the left-hand side is 226 times u, but then it was at rest, so the speed is 0. So it means 0 or u cancels out, and that means when I make v the subject, v is going to be equal to the negative of 4 times 1.5 times 10 to the power of 7 divided by 222. It wasn't necessary to substitute the value for u because u is 1.66 times 10 to the power of minus 27, but I knew it would cancel out. So you have 4 times 1.5 exponent 7 divided by 222. So that is 2.7 times 10 to the power of minus 2.7 times 10 to the power of minus 1, 2, 3, 4, 5. So this is negative 2.7 times 10 to the power of minus, so times 10 to the power of 5. So this the speed is negative 2.7 times 10 to the power of 5. The power is just to tell us that this must be in the opposite directions. Let me check again. So we have 4 times 1.5 exponent 7 divided by 2, 2, 2, 3, 5. 2.7 times 10 to the power of 5 meters per second. Okay. And then lastly, state 3 quantities that are conserved during the decay. Of course, so many quantities are conserved, but the first one could be mass energy. Remember, mass energy is one quantity. It is not mass and energy, it is mass energy. Remember Einstein's equation. The number 2, of course, momentum is always conserved in an isolated system. Number 3, we try to conserve nuclear number. Number 4, proton number and neutron number conserved. Proton and neutron number. Number 5, of course, you could say charge, but when you say proton number and neutron number, you can't again say charge. So at least you have these 3. Okay, so that is the end of paper 2.2. See you in paper 4.4. Until next time, bye bye.